Hey friends, it is .NET Conf. We're having a fantastic day too. Don't forget we've got Beginner Day tomorrow, so if you're watching now, please make sure that you share with your friends and your family that we've got 2 tracks today, 2 tracks tomorrow. One of them is Beginner Day. A lot of fantastic stuff. Right now, we have my friend Zoltan from Lombic Technologies, and he's got an amazing talk here about turning software into computer chips with HasLayer. And I'm going to be here asking your questions of Zoltan as he gives his presentation. So let's give a big virtual applause and welcome him to the show.
Thank you, Scott. It's great to be here. And I'm really sorry that I can't see any of you like it would be possible in a physical conference. But please do ask questions. Scott will tell these to me, and we can get some discussion going. So let's see what the magic is. First, just a little bit of intro. I'm from a company called Lombic Technologies. We are a software services company, obviously working a lot with .NET. Actually, we focus on web development services with an open source content management system called Orchard. Orchard runs on ASP.NET MVC, so our open source contributions are also related to that. We have quite many repositories on GitHub that you can also check out, mostly related to Orchard. We are based in Hungary, which is in Europe, so it's a little bit dark here. That's because it's 7 p.m. here, but I'm not sleeping yet. I hope you won't during my session either. Now, while we are in Hungary, most of our clients are actually foreign, from Western Europe and from North America. They also include the Smithsonian, .NET Foundation, and Microsoft itself. So surprise, surprise. And although day-to-day we do web development, we also have some research projects like HasLayer. And actually the inspiration of HasLayer comes from my university time. So back when I was a few years ago studying to be a software engineer at a university in Budapest, we also had some hardware design courses. So courses where we needed to design some logic circuits for logic hardware. And at the time it was quite cumbersome, especially for people like me who came from a software engineering background, because we have already programmed for a very long time at the time. And I really wanted to do it in C#, and I thought that there should be a way to do this in C#. Well, it's not that easy, but I started developing HasLayer at that time still. Then with one of my friends, we founded Lombic. And once the company matured, we could actually put some resources onto HasLayer to make it a reality that you can try out. Before going any further, just a word of warning. HasLayer works, and it works, well, pretty well for what it does, but it's not a mature product yet. It's not something ready for the prime time in very serious scenarios. But it's still something that you can try out and play with, and that can be useful already. So, what is HasLayer? What are we talking about? Well, HasLayer takes a computer program and turns it into a computer chip, so some computer hardware. This is what you already know, because that was also in the title of my talk. But if we dig a bit deeper, what actually HasLayer does is that it takes the logic expressed as software and tries to create an equivalent logic expressed as logic hardware from it. So basically we had some logic implemented as software, and although the hardware will be very different, the logic inside should be still the same. And all of this happens with some special chips called FPGAs. Now, FPGAs, or field programmable gate arrays, are basically computer chips that can be configured to behave like any other computer chip. So it's basically a kind of a processor that can be dynamically rewired. So for example, if you want to have a processor that will multiply matrices, then you can implement that with an FPGA. If you want to have some of the earlier Intel processors, that you can also implement with an FPGA. Again, there are limits, of course, but this is the general idea. Now, you may be a bit confused about FPGAs because these are not quite commonplace yet, but you may have already used them. And actually, I'm pretty sure you have used them in some way already, even if you didn't know it. For example, Bing, the search engine, where you can Google things on Bing, to quote a classic, that also uses FPGAs. In the background, although you can't really notice it, FPGA acceleration takes place. And not just Bing, but also on Microsoft Azure. On Azure, FPGAs are not yet public, so you can't actually access them. But behind the scenes, FPGAs are also accelerating the platform itself. And if you are talking about more closer appliances that you could have seen, FPGAs are also commonly found in network routers and other network devices. If you have visited a doctor and got an X-ray or a CT, MRI, or PET scan, then those machines commonly also have FPGAs inside them. And there's also the quite fashionable topic of self-driving cars. Now, autonomous vehicles need a lot of specialized computing power. They do a lot of things, and FPGAs are sometimes used in those as well. However, great as FPGAs are, you need to be a hardware engineer, an FPGA engineer to use them. You can't just program them with your software development skills. Just to alleviate some confusion, because you may associate onto some other devices, let's see what FPGAs aren't. For example, there is the Raspberry Pi, which is not an FPGA, although it's also a small device. It also has a visible circuit board, but that's a miniature computer. It's not an FPGA. Microcontroller platforms like Arduino or Neduino are not FPGAs either. They have system on chips and processors like bigger computers too. They have nothing to do with FPGAs. Just to give you a bit of a comparison on the merits of different computing devices, because you already know CPUs, obviously, probably you have also already programmed GPUs, but why should you care about FPGAs and Haslier? Well, because they are good at different things than CPUs and GPUs. These charts are not scientific by any means. They are just here to give you a general idea with some crude estimation. On the chart on the left, we have what degree of parallelism these different devices are capable of. Well, with purple, we have CPU. CPUs can have probably 4, 8 cores in your machine that you have on your desktop right now. Maybe twice as that logical cores if there's hyper-threading. With server processors, we have as many as 32, 40, 64 cores. There are even many core processors that are special devices with hundreds of cores, but that's pretty much the top. So CPUs don't have that many cores. However, GPUs, on the other hand, they can have thousands of small specialized computing cores in them, and those can all work in parallel. FPGAs are kind of in between. Well, FPGAs don't really have processing cores. Well, this is not entirely true, but mostly, because you design the hardware that runs on an FPGA. But depending on the capacity of the FPGA, it can house processing cores that do just the job you want them to do, in the order of magnitude of hundreds or sometimes thousands. About program complexity, so how complex can the programs be that you can write for these devices? Well, CPUs can run anything, so any complexity is possible. GPUs have a lot of limitations. If you have done some GPU programming, you know what I'm talking about. There are a lot of advances, obviously, as well, but GPUs are still very much limited compared to what you do when you program a CPU. Now, you can't really program as an application developer FPGAs, but if we talk about writing programs with such high-level tools like Haslier for FPGAs, then that's again somewhere in between. FPGAs can't do anything if you start with a high-level program than CPUs, but it can still be more flexible than GPUs. But power efficiency is where FPGAs really shine. CPUs and GPUs have their different benefits, and it really depends on the application itself, but they are more or less on the same efficiency. However, FPGAs can be much, much more efficient because they just do what you configure them to do. A generic CPU or GPU is suitable for anything, where an FPGA that you configured is just suitable for that specific task that you want it to do. And because of this, it can be very efficient. And also, FPGAs are low-power devices, consuming a couple of watts, and they are also very efficient in computing power per watt because of the mentioned very specific usage. Not to mention that FPGAs commonly are clocked on a very low speed in the order of magnitude of a couple of 100 megahertz. That also is why they are low power devices. However, there is a big downside, and that's how hard is it to utilize these devices. You can very easily program a CPU because you just need to have some basic software development knowledge. It's a bit different with GPUs, but it's very different with FPGAs. For FPGAs, software development knowledge is not enough. You need to have a hardware engineering mindset because it uses quite different paradigms. It's writing code, but that code will be hardware code that will be turned into wires and gates like AND gates and OR gates. So you have to think about a lot of other things that you have never wanted to think about as software developers. However, with high-level tools like Heslier, you can get on pretty much the same level as with programming CPUs. So that's what we are aiming for. All right, so let's get back to our train of thought. So again, what Heslier does is that it takes a computer program and turns it into FPGA logic. And not just any computer program. So we are on the .NET Conf, so probably it's not a huge surprise that we are talking about .NET programs. And the good thing is that Heslier processes .NET assemblies, intermediate language assemblies. And that means that programs written in any language that are compiled into intermediate language can be used. So not just C# and Visual Basic, but also C++, even functional languages like F#, or even scripting languages like Python and PHP and JavaScript. And all of these, well, at least in theory, we haven't tried everything, and all of these can be turned into FPGA logic. And I think it's quite mind-blowing that you can write a JavaScript script, and as the output, you will get some logic hardware. You will get a computer chip that computes the same thing that you have written in the script. All right, so far so good, but why on earth are we doing this? Because there should be a point. Well, I've already shown you the different merits of different computing devices, so to say. And FPGAs can have quite a big performance benefit compared to the other two if your algorithm is compute bound, so CPU bound, and can be parallelized massively. So if you have a compute bound, massively parallel algorithm, probably it's a good fit for FPGAs. And again, FPGAs are low-power devices, and low-power devices that just do what you configure them to do, so they can be very power efficient. Now, this doesn't matter much if you have a single computer sitting under your desk, but think about, for example, financial computations or scientific simulations that run on tens of thousands of servers. Now, whether you consume 100 watts or 10 watts, it really matters. And with Heslier, this is still only software development. You still use your .NET skills to utilize FPGAs. A lot of talk and a lot of slides, so let's see how it actually works. let me open Visual Studio. Well, if it's here. Well, I hope it's not really a surprise what we are using here for anybody. Obviously, Visual Studio is the development environment of choice for many .NET developers, although there are good ones out there that are not Visual Studio. And what we are looking at here is a quite simple parallelized algorithm implemented in a class. What this algorithm does, it doesn't really do anything useful. It's just an example, an exaggerated example of an algorithm that's very suitable to be accelerated with FPGAs and with Hasleur. What it does is that it takes an input, which will be a number, and then starts tasks. Well, we are talking about tasks, but in the end, they will be somehow translated into threads. It depends on the .NET task scheduler, how many threads will be started, but there won't be a higher degree of actual parallelism than there are logical cores in the system. On my machine, there are 8 logical cores, 4 physical cores. But we will start 280 tasks. That's a quite high degree of parallelism. While this will be translated into as many threads as is efficient on a CPU, if we turn this into hardware, there will be actually 280 independent hardware processing cores on the FPGA. So on the FPGA, we will get true parallelism. All of these 280 tasks will run actually in parallel. And what's inside these tasks is very simple. We have some conditional logic here that will be run 10 million times, and the result of this logic will be returned from each of these tasks. Then we await all of these tasks, and once this happens, we will simply sum the output of all of them. And this sum will be then the output of the whole algorithm. So before going any further, let's see how this works. I actually have an FPGA here. So let me also show this to you via the webcam. You won't see too much details, but you can see that it has some nice lights that we don't utilize at all. But anyway, here I have some low-end development board that I will use to run this algorithm. So let me start this. This is actually part of a small, simple console application. So that starts now. And hardware generation was started. So now Hasleur is taking a few seconds to create the hardware design from the algorithm. How long this takes depends on the complexity of the design. And in the meantime, the execution on the FPGA also happened, and we have some results. So if you take a look, on hardware, it took about 300 milliseconds to execute these 280 threads. If we also take into account how long it took to push the data from the host PC to the FPGA and back, then it's a bit short of 400 milliseconds. This big difference is because the communication channel that I use here is pretty slow. It's a virtual serial communication channel using a USB port, and it's quite slow. We also have Ethernet, which is faster. However, that I have here is still a low-end, relatively cheap FPGA board. It costs about $300, and it only has these two options for communication. There are much faster, higher-end boards that you can actually plug into your PCI Express slots in a computer. Obviously, those are much faster. But let's take a look on how much the CPU took to compute the same thing, and it was about 3.5 seconds. So about 10 times more, or 10 times the time the FPGA took. Now, this is not a very precise measurement because I've run this project in debug mode, and the CPU is doing some other things as well. But even in release mode and even with with being idle, it would be about 2 seconds. So still a lot more than this low-end, cheap, small FPGA board. So this should give you a general idea of what the opportunity there is. Let's take a deeper look at this example. What we see here is standard C#. There are no custom language features that we have here. There are not even attributes that you need to use. It's just standard C#. Obviously, there are limitations on what you can do in Haslyer compatible code, but it's still quite convenient. There is one piece of API that you have to use, and that's the simple memory object. Now, the FPGA board also has some onboard DDR memory. And via this simple memory object, you can access that memory space while on the hardware. And that memory space, or that onboard memory, is also used for data exchange. So if we push some data, some input from the host PC to the FPGA, that also happens via that memory. And on the way back, getting results out of the FPGA to the host PC also happens via that memory. It's very easy to use, well, hence the name simple memory. So that mentioned input that I've shown you is also read out from that memory. It only reads out a single integer, and the result is also written back to that same simple memory space. To go a bit higher up in the stack trace, we also have this extension class that makes using this parallel algorithm class a bit easier. So here is actually the location of instantiating this simple memory object. You see that it's just a simple object that you have to instantiate. You can tell it how much memory space you need. On this FPGA board, we have about 110 megabytes of user accessible memory, which doesn't seem much, but this is just for the quick access that you can use on the board itself. And we also write the input into the memory, run the algorithm, and read it back. So this here runs on the host PC. Here we push data to the FPGA, run the FPGA implemented algorithm, and read the output back. This here runs on the FPGA. This will be turned into logic hardware. And although this is a single class here, more complex algorithms can be turned into hardware as well, of course. So there can be multiple classes. You can use object-oriented constructs as well. There are limits again, but you can do a lot of stuff still. Going a bit higher up in the call stack again, this is how you would actually run the algorithm from consuming code. As you can see, it's just method calls. So we have a parallel algorithm instance, and then we call run. And that's it. Everything else is masked by Haslyer. This is possible because before this, we also have to package our parallel algorithm instance into a proxy object, so Haslyer can hijack method calls. So it's pretty fun because you need to write this single line, and after that you can keep on using your algorithm, your class instances just as usual, but in reality all these method calls will be transferred to the FPGA for execution. And it's also determined in runtime whether the execution happens on the FPGA. So you can still run your algorithm as standard.NET because it is standard.NET. You can still run it on a CPU if there is no FPGA present. You can even make Haslyer dynamically determine whether to run it on the FPGA at the time of the method call. And in the end, it can run on the FPGA. There is some further orchestration needed for Haslyer. So this is the full program class that we have in this console application. You can see, but it's not much. we need to create what we call a Haslier shell. Then there is some configuration. For example, we tell Haslier what kind of FPGA to use. This one I have here is a Nexus 4 DDR. Then we tell Haslier that we want this parallel algorithm to be accessible from the outside. So we want public virtual methods to be invocable from the host PC. We also tell it what degree of parallelism we want to have, etc., etc. And in the end, we let Haslier generate hardware from the assembly of this algorithm. So here you can see that Haslier takes assemblies as the input, not C# code, not Visual Basic code, but .NET assemblies. And I've shown you task-based parallelism in this parallel algorithm sample, but for your information, there is also operation level parallelism. Yeah, it's a pretty complicated word, and I have to say it a lot of times. But operation level parallelism means that you have an operation like addition or subtraction or multiplication or division, and you can run that in parallel for multiple items. In this case, what we have is that we have two vectors, so two integer arrays in this case, and we can add, subtract, and multiply and divide them in parallel. This is also called SIMD-like, so single instruction multiple data-like parallelism. This is what GPUs are very good at, but this way, if your algorithm needs it, you can also do that with FPGAs. And there is also a third kind of parallelism that I won't be able to show you today, but if you have multiple FPGAs, you can also utilize them in parallel. So let's get back to the slide deck. And let's dive a bit deeper. We have seen how to use Haslier as a software developer. So this is what you would use when you work with Haslier. But what is actually Haslier doing? What's the magic here? What happens when I create a Haslier shell and let it generate hardware? Well, first of all, we have an FPGA. This I already mentioned a lot of times and showed you. And this is a better picture of the FPGA board that I have here. Again, it's a Nexus 4 DDR board. It's a low-end, relatively cheap development board. So good for evaluation, but not so good for high-performance workload. We are not quite there yet. This board has many ports. One of the ports is a USB port that we have on the left-hand side. This also supplies the power to the board, and this is also used for the serial communication via a virtual serial port. Then there is also an Ethernet port at the top with the blue cable. I mentioned that you can use multiple FPGA boards simultaneously if you have multiple boards attached. And with Ethernet, this is very natural. So this is not just Ethernet, but some actual TCP/IP network communication. For example, you could take multiple FPGAs, connect them to a network switch, let Haslier running on a host PC discover all of them, and then use them simultaneously. Haslier will be able to see this device pool of multiple FPGAs and execute the same algorithm on them simultaneously. So you can not just have parallelism inside your algorithm, but also you can have multiple instances of the whole algorithm being executed on multiple FPGAs. And this here is an FPGA board, but the FPGA chip itself is that little black rectangle in the middle. That's actually the chip that does the heavy lifting. Everything else here is just serving that chip, is just here to make that chip work. On this board, as mentioned, we have some DDR memory, so there is some memory control. There are memory chips and the memory controller, of course. But since this is a development board, we have a lot of other bells and whistles as well that we don't actually use for Haslier. So for example, there is a display, there are switches. You can also see on the top right-hand side a DSUB port for analog displays. There are LEDs. So a lot of stuff that we don't need, but it's there on this board. And now let's see another demo, how all of this comes together from a hardware developer's perspective. So a bit of an insight for all of us software developers. What I'm showing to you, well, actually, let's take a look at this first. But first of all, how is the hardware actually created by Haslier? Haslier needs the tool chain of the FPGA manufacturer of the FPGA vendor to generate the gate level design. But what it creates is VHDL code. What we see here is VHDL code. Now, VHDL is a hardware description language. So this is the code that hardware engineers write. Well, there are other options as well, but you get the idea. And that, and as you can see, it was generated just a few minutes ago when I first ran the sample. And at first glimpse, it looks like some program. We have functions, we have if-else constructs, but this is not a program. This is a hardware design. And although it can look similar, but it can also look quite different, it really needs a very different mindset. Because, for example, in the hardware design, you have to think about clock cycles. If you write a multiplication, for example, in your program, you just write the multiplication and you don't care about it that much, because why would you? In hardware, a multiplication takes multiple clock cycles. So you can't just write a multiplication and expect a result. You have to wait enough clock cycles for the result to appear. So there are a lot of little things to care about. It's very different than software development. Let's take a look at the bottom of this, or more in the middle, and let's see what Haslier actually created. Here we have some type declarations. Now this is again something hardware engineers would write, and you can see that the names are something that we are familiar with. We have parallel algorithm here. There is also run, and there's a display class. Well, if you have ever decompiled intermediate language, then probably the display class is something that you heard about. Long story short, but the declarations that we see here are for the delegate inside the task that was turned into a display class by the compiler. And since we are talking about the body of the task, there should be 280 of them, right? Because we have 280 threads. And that's indeed. We have the first instance here with index 0, then the second instance with index 1, the third with index 2. And if we go all the way down here, we will find all 280 of them. So you can see here are all these 280 independent little processing cores that do the work for us in an actual parallel manner. But these are just type declarations. Let's see how one piece of code of us looks like. Because what we see here is called a state machine. Long story short, this is the piece of code that our delegate inside the task was converted into. So let's go back to Visual Studio. You remember this delegate inside the task here? Now this is what I'm talking about. And for example, here in the beginning we have this input plus index times 2. Let's see if we can find this in the hardware design. If we scroll down, we should indeed see it. Oops. And it's even here. You can see we have a number multiplied by 2, and the result of this operation, so this binary operation result variable, will then be added to the input variable. So it looks very frightening on the first sight, but this is still some kind of code that you can understand if you know where to look. And you can see that sometimes there is a pretty close mapping between the logic in the software and the logic in the hardware. And may I also point out that this code here is formatted and documented, all of this automatically. As you can see, we have comments here, and it's well formatted. So probably it's already writing nicer code than some of your colleagues. So this is the code that Hasslier creates, but how will it actually go onto the FPGA, and how can we actually execute that? Well, we need the Visual Studio of FPGA engineers for that. What we have here is a software called Vivado, which is the development environment for FPGAs manufactured by the company Xilinx, which we also use. So you can see it really looks like a development environment. And it also gives us some information. For example, it tells us what the utilization of an FPGA is, because again, FPGAs have limits. So although they are very flexible, they still can't do anything because there's just one chip of them. And you can see that the utilization of our current FPGA is roughly around 80%. So it's almost full. We can't really go above that before things get funny. And also we have some further estimations here. For example, on the power consumption of the FPGA, you can see it draws around 2.3 watts. It couldn't draw much more because it uses the USB port for the power source, and that's kept around 2 watts. But as you can see, it's very low power. And actually, yeah, so it's around 2 watts. Let's see how the design looks that Hasslier generates. What we see here, that's now in full screen. And what we see here is a kind of a helicopter view of what's on the FPGA board. That's how the components are wired together. For example, we have some connection to the DDR memory, we have connection to the USB port, and somewhere here the Ethernet is also handled. So this is how it's wired up with the communication channels. And in the middle, we have this thing called Microblaze. This is a so-called soft-core processor. It's a little processor that runs our C++ program and sits in the middle of the FPGA. We only need that to handle the communication because it's much easier to write a program for the serial and Ethernet communication than to implement it in a hardwired manner. So unfortunately, that's needed. It's not ideal, but it's there. And just below that, we can see this HAST IP. Now, this is the actual component that Hasslier generates. This is the component that is plugged into this whole design. So everything else here is only here to make this work. And it's quite complex to make all of this work. It took a lot of time to create this system just to serve that generated component. FPGA development is quite time consuming. Only specialists can do it, so hardware engineers, and there are much fewer hardware engineers than software engineers. And even if they are good, FPGA development is just much slower than software development. So you really wouldn't venture into that unless you have some very serious use case like building a PET scan, or you can use higher level tools like Haslier. Now, this is a component overview, but let's also check out what's actually on silicon. And what we can see here is the actual outline of the chip itself. So what we are looking at is the utilization of the silicon that's on there. Everything that's colored is some kind of different component here. For example, on the right-hand side, we see these purple boxes. These handle some kind of communication. These should be I/O. These somehow handle input and output. And what we have in the middle, these little blue rectangles, these are the logic cells that build up the FPGA. So actually everything here, these little rectangles provide our logic. And if we also go back here and select one of these cells here, we can also get an idea of what they actually do. I selected these two cells here, and let's take a look at what we have here. This is some information about what these cells do. Now on the very low level, so this is really the silicon level, not even the hardware design abstraction, but really the silicon. And as you can see, it's somehow connected again to our display class. It's not a big surprise that I managed to randomly select a cell that does something connected to our parallel logic to connect it to the body of the task, because, well, we have 280 hardware tasks, so most of the chip is just doing that. And as you can see, it has to do something with one of the number that's used in that piece of code. But I won't be able to tell you what exactly. So let's get back to the slide deck, because we will leave the hardware engineering landscape for now. So this is the state of Haslier, but what else do we have in mind? If you like to work with Haslier, what can you expect? What is on the roadmap? Well, for example, we have recently engaged into a partnership with the Wigner Research Center for Physics. Now, this is part of the Hungarian Academy of Sciences, and those guys are pretty smart. Most of them are physicists, some kind of physicists, and they also work together with CERN. So I'm pretty sure every one of us have heard of CERN. You know, the institute in Europe that also has the Large Hadron Collider, which they won't admit can create black holes, because obviously they can create black holes, but they won't tell you that. And the guys at Wigner, for example, have not just worked together on various research with CERN, but the Wigner campus has also one of the two data centers that are directly connected to the Large Hadron Collider and do basically all the computations for it. So again, pretty smart guys. And why we are partnering with them is to check out how Haslier can benefit science and how we can accelerate or make more power efficient scientific computations. And one of the first things we are checking out together, because it's a work in progress, is this surface growth simulation algorithm. It's quite a curious beast. It's basically an algorithm to simulate how the surface of a matter will change over time if random imperfections are in there. So, for example, this can predict how the surface of a silicon wafer used in chip manufacturing can have errors. It's an algorithm that can be massively parallelized, so we are working on that. It's not quite finished. It's not faster than a CPU implementation yet, but it's almost as fast, and still it uses just a fraction of power. But we will do some elaborate testing. We are also working on implementing a number format. Now, number format is probably not something that any of us ever thought about working on, because, well, we have integers and 32-bit floats and doubles, and even if that's not enough for financial computations, then we have the decimal and number type in .NET, but we are working on something new. The UNAM number format was invented by a mathematician called John Gustafson, and it promises to be better than the IEEE float standards that we have today. For example, it can have, with the same amount of bits, it can provide better range and or better accuracy than an IEEE float with the same size. And it also can make math actually work on a computer. It's quite funny because, for example, because there are a lot of algebraic rules that will work on paper, that will work in the classroom where we learn them, but won't work on a computer. For example, if you take the following, if you divide 1 by 3 and then multiply that by 3, then you should get back 1, right? However, what will happen on a computer is that when you divide 1 by 3, you will get something like 0.333, and if you multiply that by 3, then you won't get 1, but something like 0.9999. So it breaks math, and UNAMs also promise to be a solution for such kind of issues. It's very interesting. We are working on implementing it as a .NET library that will be also open source and usable anywhere. And it will be also usable in Haslyer because it will be Haslyer compatible. So you won't just get a new number format in a library, but you will also get hardware support for that with Haslyer. It's pretty exciting. We will do a lot of tests once it actually works. It kind of works now, but not 100%. And there's also more. We are working on adding more use cases. And I'm also asking you, dear participants, check out Haslyer. You can use it for free. Well, you need to purchase an FPGA board, unfortunately, but we are working on other options as well. And tell us how you would use it. We have some other use cases in mind as well. We are now doing some field testing of the system. It's not high-performance computing ready yet, as I also already mentioned. Eventually it will be a solution that can be used in high-performance computing, but we need to support bigger FPGAs for that. And the world is also moving into a direction where FPGAs become more accessible, and they make their way into every data center and even cloud providers. AWS, Amazon's cloud, already has virtual machines that have FPGAs, and those are even big, high-end FPGAs. As mentioned, Azure also has FPGAs, although they are not publicly accessible yet, but behind the scenes they are. And although I don't know, I would guess that eventually FPGAs will be also available as part of virtual machines on Azure. And Intel also bets on them. And because Intel, 2 years ago, if I remember correctly, acquired the second largest FPGA manufacturer called Altera. And now Intel is an FPGA manufacturer as well. And they are working on integrating FPGAs into their processors. There is already a Xeon processor that has an FPGA in the same package. And eventually there will be on the same die. And eventually, actually the processor cores will contain FPGAs too. And if you think about it, FPGAs are really about keeping up Moore's law, because CPUs can't really get any faster anymore in terms of of the clock speed, because reached the cap at a few gigahertz. They are architecturally very efficient already. We are reaching the physical limits on how many transistors and how many CPU cores we can pack on the same die. But with FPGAs, you can have application-specific processors, and that can keep up the performance increase for quite some time still. So let's wrap up. If you liked Haslier, and I really hope that you did, go and check out the SDK. It's on GitHub. Everything is documented there. It's also elaborated there on what you need to get started. But long story short, you will need the SDK, you will need the hardware project that's also on GitHub, and you will need an FPGA. And be ready, because FPGAs are really becoming mainstream and coming. And as a software developer, you will also be able to utilize them. So unless there are any questions in the meantime, thank you for your attention. And if you'd like to get in touch with me via my email address, or check out haslier.com or the mentioned SDK on GitHub, or if you'd like to learn more about Lombic itself, the company behind Haslier, check out lombic.com.
All right. Do you have a moment for a couple of questions? All right.
Yes.
All right. So Michael Earls wants to know, what are the plans for supporting other FPGAs like Spartan 6 boards and things like that in the future?
Mm-hmm. Yeah, very good question. There are plans on supporting more FPGAs, so this is just the beginning. However, we are currently evaluating what kind of FPGAs to support. So, for example, whether to support other FPGAs, and I'm most possibly talking about bigger ones and more expensive ones and current one for local development, or support the cloud provider like AWS. As for the Spartan, we haven't looked into that specifically.
Okay. A couple questions here from Conrad Kokosa, and you'll have to forgive me, Zoltan, that I don't actually understand these questions. So hopefully you'll explain them as nicely as you have explained this presentation. The first question he has is, will Haslier create or utilize additional FPGA-based memory blocks if we use arrays inside transformed code?
I'm not entirely sure I understand the question, but probably the answer is yes.
Sounds like it's pretty smart. Like, it does the right thing for parallelism, whether it be parallelism within an FPGA or parallelism across FPGAs.
That's right. So on FPGAs, there are multiple kinds of memory. There is the mentioned DDR memory that you can use with the simple memory object, but there are also some special kinds of memory like block RAM and distributed RAM. And I think the question is about that. Don't worry, this is some hardware engineering or FPGA engineering technical term. And Haslier also utilizes that as well, does as well.
He also asks a question about false sharing. I don't know what false sharing is, talking about multiple parallel operations that share data between them.
Yeah, that's so if the question is about how you can share data between concurrently running pieces of code, the answer is that unfortunately you can't. So basically how parallel execution works in Haslier is that you write your tasks, and those tasks should work with the input they get when the task is started, and they will produce the result when the task is ending. Okay. Anything in between is not supported yet.
All right, that makes sense. When I think about like the task parallel library that you were using, like task.start, I think of what Stephen Taub called delightfully parallel or naively parallel things, where you can chop them up into independent parallel streams, work streams, and then it sounds like Haslier and FPGAs work really great when those things are independent units of work.
That's right. So synchronization and locking, for example, is not supported either. Frankly, we won't support them, I think, because it would be really inefficient. What we have right now is what's the most efficient. So it would be best if if everything could be implemented in that way that's suitable for FPGAs.
All right, well, fantastic. Well, thank you so much for spending your evening with us here on the West Coast during our morning. We appreciate your effort and for all that you're bringing to the community. Thank you so much.
Thank you. Bye, everyone.
All right. Well, I'm going to go buy myself an FPGA right now, and I'm going to learn all about it with Hassler. We're going to take a short break here on .NET Conf 2017, and we'll be right back with even more. We'll be having the Peach Pie folks talk about their PHP to .NET compiler in just a moment.